Thank you. I thank the organizer for this very nice invitation. I thank also all of you who are listening to me. I'm sorry for this change in the timetable, but there were very technical issues I could not foresee and I could not test before. Okay, I would like to overview some results and to focus on the interplay between mathematical analysis and traffic modeling. And here is the plan of the talk. I hope I will be able to enter all these subjects. These three chapters are quite separated. The first will be a quite general overview. And that was meant, that is due to the fact that I understood in this meeting there are people with fairly different backgrounds. So I hope this will be of interest for all of you. Then I will focus on more recent results, and I chose two of them, which are completely different, because in the first case, we have a result that comes from traffic modeling and gave some ideas for some research also in mathematical analysis, whereas the latter one comes from the opposite way, in the sense that it is a purely mathematical analytic problem that can be of some interest also in traffic modeling. Okay. Of course, obviously, questions are welcome, and I will do my best to answer to all of them. So, traffic modeling. Clearly, I'm going to describe this interplay between mathematical analysis and traffic modeling from the point of view from my point of view, and I'm more concerned with mathematical analysis. But from my point of view, traffic modeling poses a lot of questions, and some of them are quite intriguing. And clearly, the most important questions concern safety, forecast about how traffic will be. And clearly, we would like also to run our highways or roads in an efficient way. And efficiency, in this case, as was already pointed out in the previous talk, for me this afternoon, for you this morning, was that efficiency can be seen from a collective point of view, in the sense that we may imagine a benevolent dictator, as has been said, or we can imagine that each of us is some sort of egocentric or egoistic, and each of us wants his or her own individual optimal choice. Okay, nothing bad about any of these two points of view, but both of these points of view have to be considered. And in mathematical analysis, well, clearly, from my point of view, I would like very much to say that we provide answers. That is probably too much, but definitely I think we can say we can provide tools to tackle these questions, tools to find out what can be said to answer to these questions. And this issue about tools is a very hot topic for me, because I work in a faculty of engineering, and I have very hard discussions with my colleagues, with my friends also, because very often I see engineers that strive to tackle the newest questions that arise in their own disciplines, and they keep using tools that in mathematics dated a few centuries ago sometimes. Okay, so also mathematical analysis is going forward, and I would like that newer tools can be proved to be effective also in traffic modeling, for instance. And the tools I'm going to discuss today are concerned with ordinary differential equations that give the way to microscopic models, and also to partial differential equations that typically are concerned with macroscopic models. Okay, there are other tools that mathematical analysis offers, of course, and we heard today about measure value differential equations. I did not consider them, but they are also another very fruitful and effective tool in studying the modeling of traffic. And there's a nice parallelism here between the different kinds of efficiency that one might be interested in from the traffic modeling point of view. If one pursues the collective efficiency, then he or she is led to control problems, whereas the individual efficiency leads to game theory. That is to say, in the first case, when you have a control problem, you have a benevolent dictator, which is only one and has only one goal. Whereas when you have many individuals, each of them has his or her own goal. And we clearly pass from control theory to game theory. Okay, this is a general setting. And from the point of view of ordinary differential equations, we deal with microscopic modeling. And these models are typically based on posing suitable rules for the individual behavior of every single driver. And typically, these models consist in unknowns that are this variable xi. I is the index that counts the number of individuals we are dealing with. And xi typically is the position of each individual. in the case of traffic, we usually use a straight line as a road. And these models can be, most of the time, either first-order models or second-order models. Maybe also more general than the one which is written here. They may consist of two separate equations for the position and the speed, okay? But within the framework of ordinary differential equation, we have Cauchy theorem, we have a general statement for existence, uniqueness, and continuous dependence. So through typically computer simulation or computer numerical integrations, we can try to repeat reality inside our computers. We can simulate them, we can tackle value, we can confront, compare, and study different strategies. And the literature in this field is really enormous. I just put these two papers, which one of them is quite old. I cannot pretend this is the first one in this topic, of course. And the second one is a review. Now it's already a little bit old, but at that time I found it quite useful. Then come partial differential equations. As we all know, in partial differential equations, there are many different choices of equations with completely different theories and with completely different properties. For what is of interest in traffic modeling, we are concerned with macroscopic modeling. That is to say, traffic here is described by a function, rho, which is a density, which is a function of time and space, okay? And this rho, okay, it's easy to imagine it as the number of vehicles per unit length, or better, it can be seen as the amount of space occupied by vehicles over the total amount of available space, okay? It's a density. In all my slides, clearly T will always be time. X is a space coordinate. Whenever I will talk about traffic, it will be in R. And in the case we deal with crowd dynamics, X varies in R2. And the big difference between the use of ordinary differential equation with microscopic models and the use of partial differential equation in macroscopic modeling is that in the latter case, we have a sort of reductio ad uno, in the sense that we have to find some laws that are common to all the individuals, have to reduce the variability and also the freedom of each driver to some sort of single laws that can describe a sort of average behavior, so that we can model which can be useful and which can provide usable forecasts. Okay, for completeness, I have to say that once a macroscopic model is available, in principle, using what is typically called particle path, with a terminology that we borrow from gas dynamics, using also particle path, we may get also a microscopic description, okay? But clearly this microscopic description, it is a microscopic description, but it is less variable than the one provided by a general ordinary differential equation, because in this case, this microscopic description obviously comes from these general rules that we have to impose or have to observe on the whole population, okay? Now, here comes another problem. If we want to use partial differential equation, which type of partial differential equation should we use? So as a mathematical analyst, I have to ask to experts in traffic modeling, what do they want from a model? And as you all know, the variety of answers is incredible, but I think there are a few things on which every traffic modeler agrees. And the first one is that cars are conserved. If we are describing the flow of a certain amount of cars, the number of cars should not increase, neither should it decrease. First. And secondly, another feature that I think almost everyone would expect from a model in traffic is that the speed of propagation of information, not only of vehicles, should be finite, okay? And these two properties are shared typically by conservation laws. Conservation laws, they are rooted in thermodynamics, in the dynamics of gases, and this is a general form of a conservation law, where rho is the unknown function, which is, as I said before, a function of time, which is t, and space, which is rho. And F is typically called the flux or the flow of the conservation law. And just to, I think I'm going to say something very, very elementary now, but I hope I understood this, the audience here might be very, very varied, with a lot of different knowledge present. So I will just overview a few very elementary properties of these equations. Assume we are in the simplest case where X is one-dimensional and the flow is only a function of rho, okay? So we have a scalar conservation law with an initial datum, which is this one. And okay, let's forget for a moment that I should be careful to take derivatives when it is possible and not possible. Don't worry about that. Formally, we can write this, and we want to see how the solution to this Cauchy problem behave. And consider, let's start with the simplest case. The simplest case is that in which f is linear, the flow is linear. Therefore, f prime is constant, okay? And we have this kind of evolution. That is to say, you see here on the x-axis, we have x, the space variable. On the vertical axis, we have rho, which is the density. And the initial profile is that what you see here. And these arrows display the speed with which this profile moves, okay? And if f is linear, f prime is constant, this profile simply translates and remains equal to itself, okay? And this does not happen usually in the case of traffic. More interesting is what happens here. For instance, imagine that we are given always the same initial datum, and the flow f is concave, so that f prime is decreasing. Here you see, up here we have a small speed, down there we have a big speed, because f and f prime too, they are a function of rho, and rho is along this vertical axis, okay? So if you imagine what happens to this profile when we apply this small speed up here and this big speed down there, clearly you will see that this profile gets less and less steep, okay? It becomes smoother and smoother, okay? This has, this has a counterpart in traffic modeling. Imagine traffic light turns green, from red turns green. You have a queue. Clearly, the first car, having no one in front, will accelerate at a positive speed, and the cars behind also will accelerate, but they are likely to travel less fast, to travel slower than the car preceding them. And that's how the profile forms. This is a rarefaction wave, and we expect this to be less and less steep as time goes by. A completely different situation now is when f is convex and f prime is positive. Clearly, this is not the usual case of the lighter width and Mauritian model, but just to keep the same drawing, in this case, I keep exactly the same initial datum, and I have up here, you see, a speed which is much larger than down there. And if we imagine what happens to this profile when time passes, we'll see that we have a vertical part being formed. And this vertical part is a shock, a discontinuity. You know that, I mean, if my Calculus 2 students see that I draw a function with a vertical part, they will blame me. As you know, this is not possible in mathematical analysis, but I hope we all understand each other. I mean, here there is a discontinuity, there is a jump. And as time goes by, this jump typically gets bigger. And in the case of traffic modeling, this reminds of what happens, for instance, when a traffic light turns red. Because when a traffic light turns red, clearly the first car has to stop, and also the other ones stop, and they have to decelerate, and a queue is formed. So there is here more or less a traffic light, and immediately after or before the traffic light, we have a queue at a given density, typically the maximal one. Strictly related to the fact that shocks arise is the fact that these equations provide irreversible solution, in the sense that, for instance, in this case of this queue, we get the same profile of the rho, even in case the initial data was something like that, or if it were something like that. So, and I would say this does have a counterpart also in traffic modeling, because when we see cars in a queue or a traffic jam, even if they are not stopped, if they're slowly moving, we do not understand how they were before. We just see the jam. So from this point of view, I would say that conservation laws do share several good properties with what we expect from traffic modeling in the macroscopic setting. Now, a very brief history, there are some, I would say, some nice information one can get from the history. In the case of traffic modeling, I do not pretend to draw, I'm able to draw the whole history of traffic modeling, but I would say these papers are very well known. I guess everyone in the audience knows about these papers, and they're quite old. Here, the Green Shield paper is extremely famous. Lighter width and Mauritius are the ones of the LWR model, of course. The history of conservation laws, obviously, is much longer, because it dates back at least to Euler with his studies of gas dynamics. And a big role was also played by Riemann more than a century ago. And last century, Gleam and Khrushchev provided key existence in the case of Gleam and well-posedness in the case of Khrushchev results for two completely different cases of conservation laws. I don't want to enter here now in the technicalities. I only want to say that the case of Gleam is a case in one space dimension. The case of Khrushchev is a case of many space dimensions. But Gleam applies to systems of conservation laws, whereas Khrushchev applies to only to the scalar case, okay? Now, remarkable, I would say, coincidence that always surprises me is what happened in 1995, because in 1995, a few papers came up that, as far as I understood, had a very big influence in all what followed, and probably also in what is still following, because on the side of traffic modeling, there was a very famous paper by D'Aganzo on transportation research, whose title begins with Requiem. And in this very, I like this paper, in this very nice paper, D'Aganzo criticizes very, very clearly some models, some classes of models that were stated, that were proposed, and because they had features that were not realistic. And so he declares the death of this kind of modeling. And only the same year came out also the first, as far as I know, the first paper that considered networks, road networks, by means of macroscopic models based on conservation laws. And this was a paper by Holden and Risebrough on the SIAM Journal of Mathematical Analysis. In the same year, in the case of conservation laws, was something new appeared, because especially in the case of the paper by Gleam here, we knew that solutions existed. And I remind you that the case of Gleam is a case of interest in traffic modeling, because it describes systems in one space dimension, okay? So in the case of biggest interest for traffic modeling, in 1965 up to 1995, we only knew that solution existed. We did not know if they were unique. We did not know, not really that they depended in continuous way, but we did not know in which way there was continuous dependence of solutions from the initial data. And Bressan and his group answered to these questions, first with the uniqueness of the Gleam scheme in a paper by Bressan archive, and the 2x2 case here, and then in the by-n case, there is also Benedetto Piccoli had a big role in that, okay, so a few years later. I always find it is amazing that all this happened in the same year, and these two disciplines are completely unrelated. I mean, these three papers are completely unrelated, I would say. But after that, a lot of research started, and a lot of results came up. First of all, in the modeling. The very modeling answered the models, mathematical analysis and not only mathematical analysis, answered to the criticism by D'Aganzo, introducing new series of models, new sets of models. Probably the most famous one is the model by Johan Raskell, which I briefly recall here. And I don't want to enter the details of that. It's extremely famous, very well cited paper. And it was obtained also by Zhang, essentially independently. And this model answers to the Requiem paper by D'Aganzo, showing that by means of conservation laws, it is possible to state new models that are compatible with all the observations that D'Aganzo made, okay? And here is also a very nice review about macroscopic models, again. Then another direction that appeared was that of multi-phase or two-phase models for traffic. Here I draw a fundamental diagram. By this, I mean that we have on the horizontal axis the density, and on the vertical axis here, we have the flow, rho times v. And two-phase models are settled in a set like this one, which can be, in this case, is not connected because it refers to the first model here. In other cases, it can be also connected. What is interesting is that the space where rho, the density, and rho v, the flow, can vary is on one side one-dimensional, and on the other side it is two-dimensional. And by means of a suitable use of conservation laws, we can study, use models defined on this unusual set, partly two-dimensional, partly one-dimensional. And why is it is it motivated by traffic? The reason, as all people in traffic know, is that when we have light traffic, we are typically in what is often called the free phase, where people at a given density more or less drive at the same speed, so that the density flow diagram is one-dimensional. But when the traffic gets higher, typically different people drive in different ways, or due also to traffic condition, to whatever might be, but the measured data for density and flow feel typically a two-dimensional area. And this gives rise to a variety of two-phase models, where not only here, also networks and so on. Another interesting research direction is that of macroscopic models for several populations. I know models like this were also used in some specific project with traffic data. Here we have different densities. Imagine, for instance, one density for trucks and another density for cars, or for slower and faster cars, or something like that. What is of interest is that, as far as understood from colleagues working in traffic, these models do work, or can fit very well traffic data. I signal once more that as far as I know, the full global well-posedness for a model like this one has not been proved yet, okay, from the mathematical analysis point of view. Then we have other non-local models more recently that came up. And in this kind of model, the speed depends on the density, but not on the density at a given point. One imagines that each driver is able to see a little bit in front of him or her, so that he or she can adjust the speed of the vehicle to what happens not only immediately in front of his or her, but also at a distance, okay? Another huge area that came up in recent years, definitely after the 1995 paper by Holden and Risebrough, was the study of networks. And here we have the, the book by Garavello Piccoli, which is very famous. There is an enormous literature because different authors consider different priority rules, different rules to how drivers want to maximize the flow at a junction. In some cases, buffers were inserted to obtain also well-posedness in some cases. And but thanks to the finite propagation speed typical of conservation laws, once the dynamics of what happens at junctions is understood, one can bring all of this to networks. And of course, the natural consequence of considering networks is considering the control of networks, how to manage networks so that we can obtain some sort of optimality. And by means of conservation laws and macroscopic modeling, since years, lots of researchers all around the world are considering how to manage how to control the network so that something is optimized. For instance, the travel time can be minimized, the stop and go ways can be reduced, or the flow can be maximized. And this, as I introduced before, can be done at two levels. Typically, first, in the case of controls, we imagine there is a sort of benevolent dictator that controls more or less everything so that a certain goal is obtained, or at least a certain situation is optimized. Or else we can imagine that each driver is a player, and in this case, we clearly deal with non-cooperative games, and it is natural, straightforward to look for Nash equilibrium. A very interesting research direction, I think, is to consider also both these situations in the following sense. If I'm not wrong, there was a paper by Brescia exactly on this, in the sense that the benevolent dictator, instead of directly optimizing the situation, the benevolent dictator steers the point of Nash equilibrium so that the Nash equilibrium resulting from the games played by the drivers is optimal from the point of view of the collectivity of all the drivers. And I think this is a very interesting situation, very interesting idea. I stress it so that the dictator, the benevolent dictator, steers not directly the behavior of the individuals, but steers the point of Nash equilibrium so that the Nash equilibrium is also in some senses optimal. Okay, then there were other situations with a different modeling framework in which similar techniques were applied. Probably the nearest one is that of crowd dynamics, where we have several similar problems, although the analytic techniques are very different because crowd dynamics is in two-space dimension. And then clearly there are other situations that were also considered in the previous talks of collective dynamics, floating, and so on. Okay, now I would like to enter a description of a recent result in with some mathematical analysis that is motivated by a problem with traffic modeling and is related to Brest paradox. And here we will use first the partial differential equation and then ordinary differential equation. I don't know if this is too, I always find someone who is not really completely aware of Brest paradox, so I will very quickly repeat what it is. And I apologize for those who already know about it. Imagine we have two cities, three cities, A, B, and C. And if you're going from A to C, you have to drive along these two roads. And the road from A to B requires a time which is given by the number of cars traveling through this road over 100, whereas the road from B to C requires 45 minutes, okay? Then if 4,000 cars want to go from A to C, they will need a time which is 4,000 over 100 plus 45, which means 85 minutes. Now we introduce a second road, a second possibility to go from A to C, and it's down here. And to make things simpler, we imagine that the road from A to B is essentially equal from the point of view of travel time to the road from B to C. And similarly, the road from B to C is equal to the road from A to B, so that we have similar traveling times. And these are the travel time from A to C according to the blue road, which is the upper one, or according to the black road, which is the lower one. And therefore, if we have 4,000 drivers that want to go from A to C, the situation clearly symmetric, and they will split in 2,000 passing on the blue road, 2,000 on the black road, and we will have a travel time of 65 minutes. Now imagine that another road is built from B to D, and this road is so fast that you can travel from B to D in time 0. And now, okay, to make a long story short, what happens is that drivers, being these the rules with which the travel time is computed, drivers will all go through the road from A to B, from B to D, and from D to C, because another choice would be less convenient. In fact, you see, if you go from A, B, D, C, you will go from A to B, will need 4,000 over 100 minutes. From B to D times 0, and then from D to C, another 4,000 over 100, which means 80. If one of these 4,000 drivers, for instance, once he or she gets to B, goes to C, in this second part, it will take 45 minutes. So it is not convenient. That is to say, this is Nash equilibrium. And this means that everyone will drive this route from A to B, from B to B, D, and D to C. And as you see, the situation is paradoxical. In fact, this is a paradox because with only one road, we have 85 minutes. With two roads, we improve to 65 as a travel time, but with three roads, we're back to 80 minutes. This is a paradoxical situation, okay, but it's very real in the sense that it was, there is a literature on several situations in which this was measured. The oldest one I found was in 1968 in Stuttgart. Then if you Google this, you will find this example, and you will find also other real situations in which this was measured. And no more than that, the original paper is by Brescia in 1968, but after that, in different disciplines with various realization of, for instance, different system of classical mechanics, very similar that can also produce in a classroom. We have several other instances of Brest paradoxes. Okay, so the problem I first wanted to tackle, first with Helge Holden, was: are we able to describe this phenomenon by means of conservation laws? Then the answer was yes, and we wrote down, we consider the same network, the thing that we had before, and okay, we have a theorem. I don't think it is the case to enter the technicalities of that and the general assumptions we had, but in the case we have these unusual flow density relations, then we have an explicit situation according to which for given values of the speeds on these roads, A, D, B, BC, and BD, then if these two inequalities are satisfied, then we have Brest paradox, meaning that we have a unique Nash equilibrium point, and this Nash equilibrium point is less convenient than the equilibrium with two roads. So having three roads, in all the cases that satisfy these bounds, in all these cases, having one more road is not convenient. And this can be described also by means of conservation laws. Then clearly the next step was criticism to this situation, because here we have a stationary solution, not static, but only stationary. And we wanted to see if we can have a sort of non-stationary Brest equilibrium, Brest paradox. And we did it with also Francesca Marcellini, but in a microscopic setting, that is to say with ordinary differential equation. So we use a standard follow-the-riddle model with a first order ordinary differential equation, and we impose also the usual condition. We have this small L is the length of a car. We give an initial datum where the distance between each two pair of cars is bigger than L, and we consider a rather general network, and we assign to each driver a route, which is a sequence of adjacent roads. And okay, we have to impose that there are no loops in the routes, otherwise there might be a driver trapped in this loop. And we impose a priority rule at each junction, so that this requirement, this constraint on the distance between vehicles is always satisfied as long as the two cars are on the same segment. What can happen is that we have a car very near to a junction and another one passes in front of it, and when the passing takes place, then this inequality can be not satisfied, but then the two vehicles are on two different roads, okay? Now, what comes up is that we have a theorem. We have a theorem that ensures that the system of equation we write with the system also of rules that we put at each junction provides a well-posed problem, clearly under suitable condition. For instance, that the initial data should satisfy the no collision condition, and the speed law has to be at least Lipschitz and usual, I mean, nothing unusual here. What was, sorry, I would say of some interest is that we measured with numerical integrations the travel times, and there were situations in which the average travel times or arrival times realized the Brest paradox, meaning that the situation was with traveling, I mean, bring people all choosing the Nash equilibrium with the extra road, which is less convenient than the situation with only without this middle road. Okay. Now, very quickly, I would like to give an idea of a different situation in which we have a problem in mathematical analysis that might be of some interest also in traffic. And I start from this the situation, okay, which is this is a standard notation. We have a flow for a scalar conservation law in one space dimension. This is the simplest case, and we assign a profile and a positive time. And I investigate. Now the key role is played by this set, which is the set of initial data that the initial data you note that at time capital T will give the profile W. So I assume I know the profile at time W, and I want to understand which initial datum give this profile at a given time T. And I ask these three questions, which have their own right to be considered from the point of view of mathematical analysis. First of all, when is a profile reachable? So when given W, given capital T, does there exist a U0 that will eventually yield profile W at time capital T? Then, second question, can I characterize those initial data that give as time T the solution W? As I said before, conservation laws are not reversible, so this set can be empty or can contain several solutions, several initial datum, I mean. Can we characterize them all? And finally, once we have this characterization, what are the properties of this set? Well, the situation, clearly the analytical tool here is the theory of characteristics by the Fermos, and the starting point was this implication, which is known since a long time ago because it's a classical result by Olga Olejnik, that if we know that this profile W is attained, so that if we know that this set is non-empty, then we know that this profile satisfies these that are well known as Olejnik estimates, okay, this inequality. And the first result in here with Perola is that we have the equivalence here. That is, the Olejnik estimates are necessary and sufficient to ensure that a profile is indeed obtained. Then now here the situation gets even more technical because we do have a characterization of this set of initial profile. This characterization is not really friendly to be read, but I don't think it is necessary to grasp the essence of this. Just know that there are specific exact conditions that can tell us if a profile will eventually give W a solution at time capital T. And these are given by means of integral inequalities. This is the most important case. Now, together, this information give us a lot of information on this set, and the information we have is that if we have a discontinuity at a given time, then this discontinuity will persist forever. Then we know when this set of initial data is a singleton, and then we have other properties of interest in mathematical analysis, I would say. Okay. Clearly, I only stress here that this set is, if it is not a singleton, there are cases, you see at this point here, in which this set is a singleton. When it is not a singleton, this is one of those absurd sets that live in infinite space dimension, which are very difficult to understand, to have an idea of. I skip, of course, the proofs. I only say that we use last formula, and from the analytical point of view, there is a nice connection with Hamilton-Jacobi equation. In here, what I only want to stress, so I leave the parallel with Hamilton-Jacobi equation. I only want to get back to traffic and to propose how this can maybe used, this result, and maybe might be of some interest in traffic. That to say, imagine we have a road segment and assume we have a model, a macroscopic model based on scalar conservation law that works. Okay, this is clearly not trivial as an assumption. Then assume we are able to measure at every time the inflow and the outflow from this road segment. Can we understand from Q out if something was wrong and where something happened? That is to say, since I know which profiles can actually be attained at time t, if this profile is not attained at time t, can I understand that there was an accident or there was something unusual? I can understand when did it happen along the road segment. Well, this is the problem with this Perola and tackling in this time. Of course, it's not easy to collaborate at a distance in this period, but I hope the result will be, we already have some partial result in this direction, and I hope the result will be obtained and will be of interest to also the traffic community. Thank you for your attention.